Okay, so here's a problem. This one is not in your book, so it makes a good example that you wouldn't see otherwise. It asks for the pH of a 0.25 molar ammonium chloride solution. So for starters, you need to know what ammonium chloride is. And I always harp on the polyatomic ions and how important it is that you just know them. Ammonium is NH4, and it has a positive charge. And chloride, of course, is Cl, which has a negative charge. So there's ammonium chloride's formula. Now, ammonium chloride would be formed by a reaction between ammonia, which is this, NH3, ammonia, ending with an A. Ammonium, UM, is the protonated version of that. It's got a fourth hydrogen and a positive charge. So what happens here is that ammonia, which is generally a gas, will meet up with this bright green hydrogen chloride, or hydrochloric acid if it's in aqueous solution. And what's going to happen, I think you know, is this is going to be the acid, so it's going to donate the proton, and ammonia is going to serve as the base and accept the proton. So the hydrogen is going to break loose from the chlorine. In other words, this hydrogen chloride molecule with a covalent bond is going to separate into two ions, a hydrogen ion with a positive charge, which we also call a proton, and a chloride ion. It's negative because it has hydrogen's electron, the pink X there. Chloride is the conjugate base of hydrochloric acid, which is a strong acid. Very weak base then. Strong acids have weak conjugate bases and vice versa. Then the ammonia will say to the hydrogen with the positive charge, come on over here and I will share this pair of electrons with you. And of course that is called a coordinate covalent bond or a dative bond, and that gives us over here to the everything to the left of the vertical blue line is ammonium, and to the right of the vertical blue line is chloride. Okay, ammonium chloride. So ammonium chloride is a salt of the base, weak base, ammonia. Let's write this down. Ammonia, weak base, and hydrogen chloride, or again, if this were dissolved in water, we'd call the solution hydrochloric acid. And it is a strong acid. Strong acid. I'm going to call it hydrochloric here. Hydrochloric acid, a strong acid. So when a strong acid and a weak base encounter each other and neutralize each other to form a salt, and by the way, notice there's no water in this one, but that's okay. So we have formed a salt. Now, will that salt be basic or acidic, since it's the offspring of a strong acid being neutralized with a weak base? Well, the strong acid's going to win. So this salt is going to be acidic. Acidic. Strong acid wins over weak base. Okay, so we're taking that information over here. Strong acid wins over weak base, making an acidic salt. Okay, so why acidic? How is this acidic? Well, ammonium, NH4, is the conjugate acid of ammonia. Now remember, to find a conjugate acid, you add a proton to it. To get a conjugate acid, you add a proton. Well, Well, we took this proton and added it to ammonia to get ammonium. So this is the conjugate acid of this base, ammonia. But this acid then can give that proton back. It can donate it. So it will donate it to water. And that will cause what we always see acids causing, and that is the production of hydronium. And what do we get? When this conjugate acid donates a proton, when we move one of these hydrogens over to the water, what's left of this? What's the conjugate base? It's ammonia. Okay? So it's the production of these hydronium ions that makes this thing acidic. So this is now a weak acid, and it is donating a proton to water to form hydronium, which is what acids do, and leaving behind its conjugate base, which is ammonia. So if ammonium chloride is 0.25 molar, then when it splits, since there's one ammonium and one chloride, matter of fact, let's do this. Ammonium chloride will split apart into the ammonium ion and the chloride ion. Okay. Then for every one of these, we get one of these and one of these. So for two of these, we get two of these. If this was 10 molar, this would be 10 molar. Since this ammonium chloride is 0.25 molar, the ammonium is going to be 0.25 molar. So I'm going to bring that down here. That initially, our ammonium concentration is 0.25 molar. And until it starts donating protons to water, we have essentially no hydronium and no ammonia. So those are our initial conditions. And so, of course, the change is going to be, we're going to remove X of this to create X of this and create X of this, so that at equilibrium we have 0.25 minus X, X, and X. And our K is going to equal hydronium times ammonia over ammonium. Now, this is acting as an acid, so we need a Ka. We need the Ka for ammonium. Well, if you flip over to a table of Ka values, you will find nothing. You will not find Ka for ammonium. We've seen this situation arise before. What you can find Kb for ammonia. So, let's say this over here. We need Ka for ammonium. We can't find it. But we can find Kb for ammonia. All right. So I don't have my book right here with me to show this to you. I'm going to round this one off because I think that's what our book does. For ammonia is 1.8 times 10 to the minus 5. Now this text actually calls it 1.76, but I believe 1.8 is close enough. Okay, now the relationship to remember. And the first time I showed you this, I said this is going to be real important for you to remember. The Ka for an acid times the Kb for its conjugate base. So you take a conjugate acid and base like ammonia and ammonium. Ka for the conjugate acid times Kb for the conjugate base always equals Kw. You have to remember Kw is 1 times 10 to the negative 14. You simply have to know that. KB here is 1.8 times 10 to the minus 5. So Ka times 1.8 times 10 to the minus 5 equals 1 times 10 to the minus 14. So we'll divide each side by the 1.8. That'll cancel it out on this side. So Ka is going to equal, let's see what we get here. Let's clear that. And we need 1 times 10 to the 14 negative divided by 1.8 times 10 to the 5 negative, and that gives us 5, and repeating 5s forever. So I'm just going to say 5.6. I'm going to round that up at that end, and it just rolls everything over. So 5.6 times 10 to the negative 10. So there's my Ka value for ammonium. Okay? Ka for ammonium. So I'm going to bring that over here, and we're going to say that 5.6 times 10 to the negative 10 equals, hydronium is represented by X, ammonia is represented by X, and the ammonium concentration is 0.25. Again, it's actually 0.25 minus X, but since our Ka is this small, we know that that X is going to be ridiculously small. We'll just ignore it. That'll make the calculations easier. Yeah, it turns them into estimates, but that's okay. It's close enough. So we need to multiply both sides by 0.25. Half of 5.6 is 2.8, and half of that again is 1.4. So 1.4 times 10 to the negative 10 equals X squared. So we take the square root, which means about 1.2, won't it be? 12 times 12 is 144, so 1.2 times 1.2 is going to be about 1.4, maybe a little less than 1.2. I'm just going to go with that. Times 10 to the negative 5. Square root of something to the minus 10 is going to be something to the minus 5. Tell you what, we'll do this. We'll multiply this times 0.25, and then we'll take the square root. And it's 1.178 or 1.18, like I said, a little less than 1.2. And 10 to the negative 5th, we've got 4 zeros there, so the decimal would fall right there. So yeah, so that's good enough. So this is X, and that is here, so it's this. So how do we find the pH? It will be the negative log of the hydronium ion concentration, which happens to be X, which happens to be 1.2 times 10 to the minus 5. And that's going to be about 4.8, 4.9. We hit the log button. We've still got the number in here. This number, of course, is not rounded off, so it'd be a little bit different if you actually punch 1.2 times 10 to the negative 5 in there, but I'm just going to go with it while I've got it. Log and change the sign, change the sign, so 4.9. Remember, we want the negative of this negative 4.9. Negative of the log. The log is negative 4.9, the negative of that is 4.9. What if we had 1.2 times 10 to the negative 5th? If we had taken that where I rounded it off and done the log of that, still get 4.9. See, it's not that different. Okay, so that's a good problem. And let's see, yeah, I can't get the whole thing on the page in the view at once. I guess that's got it. So there's a way to find the pH of Ammonium chloride, which what we had to know about it is what it is, NH4Cl. We were able to take a look at why it is a salt, and since we figured out that it was the salt made from a weak base with a strong acid, we knew it was going to be acidic. Now, there are other ways to do that, but that's just the easiest way to think it through as far as I'm concerned. The textbook will say something like ammonium is the conjugate acid of the weak base ammonia, so it will be a weak acid, and chloride is the conjugate base of a strong acid, making it a very weak base, so it will not play any role in determining the pH. And I'm like, okay, let's just go with this. So ammonium with water forms hydronium, and ammonia has the conjugate base. So there you go. That's that problem. That's a good one. And so you've now seen a couple of examples of finding the pH of a salt.